Okay, next let's go to this one. Determination of the spring constant of a helical spring. Okay, so let's look at the derivation first of all. Now it's like this. Like let's say if you stretch this, okay, if you stretch this helical spring, right, it will create a tension inwards, right? That means if you give your displacement this way, the force will be created in the opposite way, right? Force will be created in the opposite way. Okay, so we can say F is equal to ma, and this F is, it's not kx, it is minus kx is equal to ma. Therefore, A is equal to minus k over m times x. Okay, so according to the characteristic equation of simple harmonic motion, which is A is equal to minus omega squared x, omega will be root k over m. Therefore, we can say T is equal to 2 pi over omega. So T is equal to 2 pi, these things go upside down, root m over k. I hope it is clear, right? So this is how we get this, right? So this practical is also just like the above one, like you do the thing for 20-30 oscillations and then get the reading for time period, and then you divide it by the number of oscillations and you can get the value for time period. Here also what we do is like we use a spring, we attach certain masses to it, right? We attach certain masses to it, okay? And then this is our independent variable, okay? This is our dependent variable, okay? According to this simple lemma, we look at how this t squared will vary, and then we plot a graph, okay? And this graph's gradient, okay, this graph's gradient is given 4 pi squared over k. So we can say k is equal to 4 pi squared. The spring constant should be determined or gradient. It's very simple, right? Just like the bubble. Okay, then these points, just remember, can we have large displacements? No, because otherwise the spring will compress and equation won't be valid. This equation is also valid for small displacements. Okay, for small displacements only this equation is also valid. And next, this is the way of measuring, right? Normally we keep a pointer and a ruler little bit to the right or left, and then we measure. Okay. Here also errors. For the reading, we take the total time for oscillations. Okay. Another way to minimize the extension. So here, like we should now in simple pendulums, we should try our best to minimize the angle, the theta. Okay. But we can do that by using longer strings. So remember those answers, right? Why take longer strings? Now they can ask it in another way, like give us a way that we can increase the accuracy of the experiment. Okay, then you can suggest we can use longer strings. So these questions and answers can be swapped as well when they ask, right? So don't always remember one way. Just get the idea properly. There should be a little bit of memorizing, that is true. Okay, so here another way to minimize extension, we can use a lower mass. If you use a lower mass in this practical, it won't extend a lot, right? Let's look at this as well. See, this is what we do. When you change the mass, the time period changes accordingly. Okay. When you change the mass of the total spring. Right. So this is how it comes. It's a very short practical.